In these slides, we're going to derive the expression for the capacitance of parallel plate capacitor. So the sequence of steps that we're going to follow is the same when you want to calculate the capacitance for any kind of capacitor, but let's just illustrate the steps. So first you assume a charge plus Q and minus Q on the conductors. Then you calculate the potential difference between the two conductors, and from this expression of the potential difference you'll be able to find the capacitance, because the charge will appear here somewhere, and you have charge and you have potential difference. When you take the ratio of those two, you'll get the capacitance. Let's see how these three steps work in reality and for this particular problem. So in this problem you have two parallel plate capacitor, two parallel plates, plate number 1 and plate number 2, and of course there's an electric field between them. We're going to assume that the electric field is uniform in the region between them, so we're going to use the expression for the infinite sheet to get the electric field. This is an approximation, but we're going to do that approximation. So the first step, as we mentioned, is to assume a charge Q on one plate and minus Q on the other. That means there's some electric field going from plate 2 to plate 1. Now the second step, to calculate the potential difference between the two plates. Let's find the potential on the plus plate minus the potential on the minus plate, which has to be a positive number. So we've done this integration before in detail in a region where the electric field is uniform. Do you remember what the answer was for the potential difference? The potential difference was the electric field times the distance. The distance in this case between the two plates. Okay, and also before in the chapter on Gauss's law we found what the electric field was for infinite sheets, between two infinite sheets, one with charge plus Q and one with charge minus Q. So can you remember what the electric field was in this region? The electric field was sigma over epsilon naught. Sigma is the charge per unit area, so sigma is Q over the area of the plate, and so we can substitute then E as Q over A epsilon naught into this equation, and we get this final relationship, that the potential difference between the plates is related to the charge and these variables also. So from this expression, what is the capacitance of the device? Well, we know the capacitance is Q over delta V. So here you have Q and here you have delta V. So if you take the delta V and you divide here by delta V, so you get Q over delta V, that means you have to send the epsilon naught A up there and divide by D. So that means Q over delta V is basically epsilon naught A over D. And as we see here, the answer, the capacitance depends only on the geometry. It depends only on the area of the plates and the distance between the plates. It doesn't depend on the value of Q or delta V itself. The ratio always remains the same. Remember, if you go back to the first video on capacitance, no matter how much charge you put on the plates, always the charge over potential difference will be a constant. And this constant value depends only on the geometry. So if you keep the geometry fixed, then the capacitance has a certain value.